Hi, I'm Dr. Jason Brinkley, and this is the pH scale. By the end of this video, we will be able to calculate pH from solution concentration data and calculate hydronium and/or hydroxide ion concentration from pH data. So the pH scale is a way to measure acidity or basicity of a solution using a range from 0 to 14, where 0 is extremely acidic, 14 is extremely basic, and 7 being a neutral pH. Okay? pH is something that you've heard of before. It's very often talked about in products, skincare products, and things like that. The idea is that the addition of an acid to water increases the hydronium ion concentration and decreases the hydroxide ion concentration. We saw that in the last video talking about the ionization constant of water, the Kw. And the addition of base to water decreases the H3O by increasing the hydroxide ion concentration. So this is when you have an acidic solution. This is when you have a basic solution. And when the concentrations are equal, this is when you have a neutral solution. Okay? pH measurement can be done in a number of ways. The most common is colorimetric or potentiometric. Colorimetric titration, colorimetric pH measurement is done using something like pH paper or an indicator solution. You can see here we've got a solution of sodium hydroxide, and when we add a drop of that to pH paper, it turns dark blue, indicating that the pH is probably somewhere around 11 or 12 in terms of this pH paper. If we were to add an acid, we would see it turn red. Okay? Now, the potentiometric titration is we take sodium hydroxide, potentiometric measurement, not titration. I keep using the wrong terminology. The sodium hydroxide is put into a beaker, and we add an electrode that measures the hydrogen ion concentration. And you can see here that the solution is 10.13. Potentiometric is going to be more precise than colorimetric will be. Okay? But colorimetric is often used just to get an idea as to whether you have an acid or a base. Now, pH calculations. The P in pH is an operator. Okay, what's an operator? An operator is a mathematical term to denote doing something to a number. In this case, we are taking the negative log of something. The negative log of H, or H3O plus concentration. So pH is equal to negative log of H3O plus concentration. Something like PCl would equal the negative log of Cl minus concentration. Or POH would equal negative log of hydroxide ion concentration. So that P just means negative log of. Okay? So mathematically, we're taking things that are really small, usually like the concentration of hydronium or hydroxide ions in solution, and turning it into a decimal number, okay, a number that's fairly large. Okay, that's what the logarithm does. It takes the small number and makes it like a decimal. Okay. So let's calculate the pH of a 1.0 times 10 to the minus 4 molar solution of HNO3. So what I will do is I will write pH is equal to negative log of the H3O plus concentration. Now HNO3 is our strong acid. Therefore, it dissociates completely into H plus ions in water. So H3O plus NO3 minus in water. So we're taking this and we're finding that. So the concentration of the H3O plus is the same as the concentration of the HNO3, 1 times 10 to the minus 4. So this is equal to negative log of 1.0 times 10 to the minus 4 molar, which, when we do the math, is 4.00 pH units. Now, a word about significant figures. This number has 2 sig figs, but Dr. Brinkley, it looks like it's got 3. It looks like that, but the number before the decimal place is a placeholder. It is these 2 decimals after the digits that correspond to the 2 digits in our concentration. Okay, so however many significant figures, number of significant figures in the concentration equals the number of decimal places. After the placeholder. Okay? Let's calculate the H3O plus concentration of a solution that has a pH of 5.0. So we know that pH is equal to negative log of H3O plus concentration. So we also know that HNO3 is a strong acid, which means that all of the HNO3 has gone to H3O plus. And we know that pH is equal to 5. So if I do my math here, I get pH of 5.00 equals negative log H3O plus concentration. Now, I'm going to rearrange this equation a little bit. I'm going to move the negative sign to the other side. To get that. From that, I'm going to use the anti-log. Okay? The anti-log button is usually found on your calculator above the log. You usually hit second log to get the anti-log. Or it might say something like 10 to the x. So that is the anti-log key. I'm going to apply the anti-log to this. So I get 10 to the minus 5.00 equals 10 to the log of H3O plus. The log and the 10 cancel, and that gives me H3O plus concentration equals 1.0 times 10 to the minus 5 molar. And that's our answer. 1.0 times 10 to the minus 5. Let's calculate the pH corresponding to a 1.0 times 10 to the minus 2 molar of solution of sodium hydroxide, and 1 corresponding to a pH of corresponding to a 1.0 times 10 to the minus 6 molar solution of sodium hydroxide. So there's a couple of ways we can attack this. We can say, okay, I know the concentration of hydroxide ions in A equals 1.0 times 10 to the minus 2. I know that Kw is equal to H3O plus times OH minus concentration, and that is equal to 1.0 times 10 to the minus 14. So I can plug in my hydroxide ion concentration and get the H3O plus concentration. So if I do that, I get H3O plus is equal to 1.0 times 10 to the minus 14th over 1.0 times 10 to the minus 2, and that equals 1.0 times 10 to the minus 12. And if I take the pH of that, take the negative log of that, negative log of 1.0 times 10 to the minus 12. That equals 12.00 pH units. Okay. Similarly, for B, the OH concentration is equal to 1.0 times 10 to the minus 6th molar. I should write molar there so that we know the concentrations. Kw is equal to H3O plus times OH minus. We're going to plug that into there, which equals 1.0 times 10 to the minus 14. And we get the H3O plus concentration is equal to 1.0 times 10 to the minus 14th over 1.0 times 10 to the minus 6th is 1.0 times 10 to the minus 8. Take the negative log of 1.0 times 10 to the minus 8. That equals 8.00 pH units. So we can see that as the concentration of hydroxide decreases, so does the pH. Now let's calculate the H3O plus concentration corresponding to pH 8.5 and corresponding to pH 4.5. Now you can see in the previous examples that everything was a perfect number. And that has to do with the power of 10 that we were dealing with. We were dealing with perfect powers of 10. 1 times 10 to the minus 4th, 1 times 10 to the minus 6th. That is easy to calculate logs, okay? But you can do it with numbers that aren't perfect as well. So we talked about pH equals negative log H3O plus concentration, and that is equal to 8.50 equals negative log H3O plus. So this is for part A. Move the negative sign to the other side. Negative 8.50 is equal to log of H3O plus. Take 10 to the power. That cancels out the logs. And we get 10 to the negative 8.50 equals the concentration of H3O plus, which is equal to, now this is where I actually have to pull out my calculator and do this problem because the numbers are not perfect. So 8.5 negative anti-log, and we get 3.1, or actually 3.2 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9 molar. For part B, pH equals negative log H3O plus, which is equal to 4.50 equals negative log H3O plus. Move the negative sign, negative 4.50 equals log H3O plus. Take 10 to the power, the anti-log button. The logs cancel, and we get 10 to the negative 4.50 equals the concentration of H3O plus. And 4.5 negative to that power gives us the H3O plus concentration equaling 3.2 times 10 to the minus 1, 2, 3, 4, 5 molar. Let's calculate the pH of a sample of blood that has an H3O plus concentration of 3.3 times 10 to the minus 8 molar. So pH equals negative log of concentration of H3O plus. So this is negative log of 3.3 times 10 to the minus 8th, which is equal to, so I take 3.3 E e to the negative 8, and I take the log of that. And I get 7.48 pH units. Remembering that the number of significant figures is the number of decimal places at the end of our pH measurement. So I hope you've enjoyed this foray into pH, the pH scale, and I look forward to seeing you in the next video.